If you're truly interested in music production and have extensively searched online for valuable tips on precisely how to significantly improve your tracks, you've probably come across numerous discussions about linear phase equalizers, whether you should always, consistently use them, never ever use them, or only in certain specific situations. If these conflicting pieces of information have left you confused, we're here to clear things up. In this video, we explain how linear phase equalizers work and when and how to use them. All equalizers basically perform three tasks. They effectively change the gain of a specific frequency band, introduce a noticeable delay or phase shift, and additionally add ringing. If we choose to use an EQ, it's clear that we want to change the gain of certain frequencies, but as a result, we also get the other two effects. These three aspects are interconnected, to the point that they essentially represent three different ways of describing the same operation: equalization. While understanding the change in gain is fairly intuitive, to have a truly complete picture of precisely how linear phase equalizers actually work, it's absolutely necessary to understand phase shift and ringing. The phase of a wave indicates its position within the cycle at a given moment. It is measured in degrees from 0 to 360. For our perception, the absolute phase of a signal is not that important. What matters much more is the phase difference between two or more signals. This too is measured in degrees from -180 to +180. This is because when we sum multiple signals, the phase difference can affect the amplitude of the sum. Every time we equalize a signal, the equalizer alters the phases of some of the harmonics, delaying or advancing them. To better understand what happens, let's imagine a signal made up of these harmonics. Notice how, at the beginning of the sound, they all have their phase at 0 degrees. Let's observe the highlighted harmonic. After passing through an equalizer, we see that at the output it undergoes a phase shift and no longer starts at 0 degrees. Let's do the same test with a real sound. Let's take a kick drum hit and put it on two different tracks. We equalize one of the two tracks and compare the waveforms. We notice that the equalized one is shifted compared to the original due to the action of the EQ. The phase difference between two signals can be represented in a graph like this, where the x-axis shows the sound frequencies and the y-axis shows the degrees of shift. A straight line indicates that there is no alteration of the phase of the signals. The frequencies enter and exit the EQ while maintaining their original phase relationships. A graph like this, on the other hand, indicates that some frequencies exit the EQ ahead of time and others with a delay, altering the original phase relationships. As we can see, phase distortion becomes more evident the more extreme the EQ settings are. Lately, a lot of attention has been paid to this phase distortion, perhaps precisely because of its name, distortion. However, this distortion is not a side effect or a flaw of the equalizer, but rather an integral part of the equalization process. Phase distortion is essential to achieve the desired equalization curve. It's important to emphasize that it's not the equalization that causes phase distortion, but rather phase distortion that causes equalization. Without phase distortion, it would not be possible to achieve any equalization at all. This phenomenon is present in both analog and digital equalizers. In analog equalizers, it is the reactive components such as capacitors and inductors that cause a phase shift in the signal. In digital equalizers, the same effect occurs due to the way samples are processed. Phase distortion in digital equalizers is therefore not a simulation to emulate analog sound, but a necessary effect to achieve a specific equalization. Once you understand the issue of phase distortion, it's fairly straightforward to see how to eliminate it in order to achieve linear phase equalization. If we carefully look at this image once again, it's not difficult to clearly see that if we run the audio signal that has just come out of the EQ back through the very same EQ, but in a completely reversed manner, all the harmonics will return to their original phase. In fact, the specifically highlighted harmonic, which was initially delayed at the EQ output, will now be ahead after the signal is carefully reversed, and a second pass through the EQ with precisely the same settings will delay it once again, effectively bringing it back into perfect phase with the others. For example, instead of boosting 1000 Hz by 4 decibels in a single pass, we can apply 2 decibels in the first pass, invert the signal, add another 2 decibels in the second pass, and finally invert the signal again. In this way, we've applied the same total equalization of 4 decibels, but in 2 passes, thus eliminating phase distortion. This is the concept behind linear phase equalizers. Let's look at a practical example. Let's take the same kick drum hit from the previous example and put it again on 2 tracks. To avoid being distracted by gain variations, we'll only modify the phase of one of the kick drum hits using a specific plugin like Melda Productions Freeform Phase. Let's configure the plugin as we like and always keep the same settings. We apply the effect to the track and observe how the phase shift compared to the other is clearly evident. Now let's apply reverse once, then the freeform phase again, and finally reverse a second time. We can notice how the kick drum hit is back in phase with the original one, due to the 2 phase shifts that are equal but opposite. This solution works, but it comes with a major problem. It can't be applied in real time, because to do the reverse we first need to have the complete signal. So it's not an acceptable solution, because when we're working with an EQ we want to hear the result as we work, not afterwards. Among EQs that work in real time, we distinguish between 2 categories. There are minimum phase EQs, which inherently cannot eliminate phase distortion, and linear phase EQs, which are specifically designed to correct phase issues. All analog equalizers, and indeed most digital ones, are minimum phase, while only some specialized digital equalizers are truly linear phase. So, real-time linear phase is exclusive to the digital world, and the only way to achieve it with a minimum phase EQ is to use the double reverse method just mentioned. To continue and understand how linear phase equalizers work, it's necessary to grasp the concepts of impulse response and ringing. A signal can be represented graphically in 3 dimensions: frequency, amplitude, and time. So we would need a 3-dimensional graph like this one, but more commonly we use 2-dimensional representations like these. In this one, we see how the amplitude varies over time, whereas in this other one, we see the amplitude of the frequencies that make up the signal. It's important to understand that these are 2 complementary representations. If a signal exists in the frequency domain, then it also exists in the time domain, and vice versa. In fact, we can switch from one representation to the other using formulas like the Fourier transform and the inverse Fourier transform. In short, the same signal can be visualized both in the time domain and in the frequency domain. This is the same as this. One thing that's often unclear is that the equalization set on an EQ actually corresponds to a real signal. However, this signal is virtual, so to speak, and exists only when there is another signal entering the EQ. We are used to seeing this signal in the frequency domain, but as we've just said, it also exists in the time domain. To observe it, we send an impulse, that is a signal made up of just one sample, into the input of the EQ. What we get at the output is the impulse response of the EQ, which represents the equalization in the time domain. In fact, if we analyze this impulse response with a spectrum analyzer, we once again see the equalization curve we've set. In practice, what an EQ does is combine 2 signals, the input signal and the impulse response, which represents the equalization. In the previous example, the EQ combined the impulse and the impulse response. However, we know that a digital signal is made up of a succession of impulses, so the EQ combines each of these with its impulse response. Depending on the type of impulse response, digital filters can be of 2 types: infinite impulse response and finite impulse response. IIR filters are similar to analog ones because they combine the samples using a feedback circuit. That is, they take the output sample from the EQ and send it back to the input. For example, if the feedback sends 50% of the output signal back to the input, the new output sample will contain 50% of the one that just came out, and therefore a certain percentage of all the samples that have previously passed through the filter. With each round of feedback, the contribution of the first sample decreases but never becomes 0, thus creating an infinite loop. This means that the first input sample also influences the last one due to the continuous feedback. Because of how they work, IIR filters are light on the CPU and introduce very little or no latency. The impulse response of an IIR filter looks like this. The additional oscillations are called ringing, and they are what gets added to each sample of the signal to equalize it. Since the oscillations follow the input sample in the EQ, this is called post-ringing, but we'll come back to this later. FIR filters are exclusive to the digital domain and have no analog equivalents. They work without using feedback circuits, combining only the input samples without considering the output ones. This process is called convolution and is also used for other effects such as reverbs and amplifier emulators. It's a complex topic and we'll explore it in more detail in an upcoming video. Unlike IIR filters, FIR filters require a certain number of input samples before processing the first sample. For example, they might require thousands of samples before starting processing, and this can cause considerable latency, which can exceed 1 second. However, the higher latency due to a greater number of samples allows for better filter quality, especially at low frequencies. We can compare the behavior of the two filters in a graph. If we send only a single sample as input, we can see how the response of the FIR filter is actually finite in time, while that of the IIR continues indefinitely. Hence the names finite impulse response and infinite impulse response. The distinctive feature of FIR filters is that it is not necessary to wait for the output signal from the equalizer. As a result, it is possible to manage the phase and gain of the filters independently. This is in contrast to IIR filters, which depend on the feedback from the output signal and therefore do not allow for separate control of phase and gain. So let's move on to how an FIR filter manages to achieve a linear phase at the output. Since its impulse response is finite, we can intervene without having to wait for the entire signal. It's enough to have just a portion of it. As we saw earlier, if we pass a signal twice through an EQ with 2 reversals, we end up with a linear phase at the output. Although in a slightly different way, this process can only be replicated in real time with FIR filters. We have also seen how an equalization curve corresponds to a signal in the time domain. If, within a FIR filter, we apply a reverse to the impulse response before combining the two signals, we get the same result as if we had reversed the input signal. So if this impulse response causes a delay in one frequency band, the other causes a mirrored advance. By combining the two impulse responses, it's as if we make the signal pass through the EQ twice, once normally and once in reverse. Only instead of inverting the signal as we saw earlier, we invert the equalizer itself. However, linear phase introduces several typical problems of this type of equalizer. Let's see what they are. IIR filters require relatively few calculations to work, usually about 5 multiplications for each sample of the signal to be processed. This is because the feedback present in the circuit allows it to take into account all the multiplications done previously. In FIR filters, on the other hand, many more multiplications are needed precisely because there is no feedback. In fact, to calculate one output sample, a FIR filter needs to use quite a few input samples. The greater the number of samples taken into account, the higher the precision of the filter. It is therefore not uncommon for even tens of thousands of samples to be used for its operation. As a result, a FIR filter requires a high number of multiplications for each input signal sample. Even with all the various optimizations that developers can introduce, the resource consumption of FIR filters is definitely higher than that of IIR filters, both in terms of CPU and RAM. As we have already previously mentioned, using a very high number of input samples results in significant latency, and the entire input signal is significantly delayed as it precisely passes through the digital filter. The amount of delay depends on the filter's resolution. For example, the FAB filter Pro Q3, when set to linear phase at the highest resolution, introduces more than 66,000 samples of delay, which is equivalent to about 1.5 seconds. This excessive latency makes any processor unusable during recording or in any situation where low latency is required. Normally, during mixing, the latency introduced by plugins doesn't cause any issues because it's automatically compensated for by the DAW itself. The problem, however, is that latencies of this magnitude can't be compensated for by all software, and even when they are, it results in a huge delay being introduced across the entire session. As a result, in the case of the latency introduced by the Pro Q3, any change in the session would take about 1.5 seconds to take effect, making it difficult to work. You can always reduce the filter resolution to decrease latency, but this affects the quality of the filter itself, especially in the low frequencies. In fact, FIR filters are able to work on a number of frequencies equal to half the number of samples considered. For example, with 4,096 samples, you have 2,048 frequencies available to work on, which means 1 every 10 between 20 and 20,000. This creates problems in managing low frequencies, because due to the logarithmic distribution, there are very few frequencies to work on, while it doesn't cause major issues in the mid and high frequencies. We see the same effect on any spectrum analyzer. The resolution in the low frequencies is lower than in the high frequencies. By increasing the samples to 8,192, you have 4,096 frequencies available, which means 1 every 5 between 20 and 20,000. Better, but the resolution in the low frequencies is still not adequate. The ProQ3 in linear phase low mode introduces a significant latency of 3,072 samples, so at most it can effectively utilize 3,072 samples for its internal calculations, which is definitely not nearly enough to properly work on the very low frequencies. In fact, if you try to make any adjustments with this setting, it's easy to get distortion or artifacts in the low end. Regardless of the latency and the increased load on the CPU and RAM, we can choose to increase the filter resolution to work better on the low frequencies. Even this way, unfortunately, we haven't solved all the problems. In fact, when working on the low frequencies with higher resolution, another side effect of linear phase filters becomes more apparent. Pre-ringing. As we've seen, what a filter does is replace each sample of the input signal with a copy of the impulse response multiplied by the sample itself. However, in FIR filters, the impulse response is symmetrical, and this leads to the introduction of an artifact called precisely pre-ringing. Let's consider this signal and focus only on the first sample. As we said, this is replaced by the filter with a copy of the impulse response. We can see graphically that by making this substitution in an FIR filter, there will be samples that precede what was originally the first sample of the signal. In reality, those samples are what cause the latency of FIR filters, and the first sample would be delayed, even though in a DAW this latency is compensated for within its capabilities. The set of these samples introduced by the filter creates pre-ringing, which is perceived as a kind of echo or fade-in that precedes the start of the sound. An effect that is impossible to occur in reality. As we've seen, the amplitude and duration of the impulse response depend on the equalization settings, and the more extreme the adjustments, the more evident the pre-ringing becomes, especially in the low frequencies. With this equalization, it is clearly noticeable. And by rendering the EQ, we can also see it. Minimum phase filters introduce only post-ringing, while linear phase filters cause both pre- and post-ringing. Let's try to understand the difference between the two. Post-ringing is not very bothersome to the ear because it usually has a low intensity and is easily masked by the sound itself. Moreover, it's a phenomenon we're used to because it happens constantly in everyday life. Let's take an example. Now we're in the recording room of the Absonance Studio, a space with controlled acoustics where most of the sound is absorbed. If we pop a balloon, what we get is the equivalent of an impulse, that is, a sound with high intensity concentrated in an extremely short period of time. Since we're in a treated environment, what we hear is basically just the impulse because reflections are minimized. From the waveform, you can see that the energy is concentrated in a single instant and does not continue over time. Now instead, we're in the main hall of Absonant where we hold most of our lessons. This environment is not acoustically treated and the sound is reflected by the walls. If we pop another balloon here, we expect to hear a reverberation tail. We can also see how the waveform lasts longer than before. This reverberation can be considered as the impulse response or the ringing of the environment, and it doesn't bother us. On the contrary, it actually gives us information about the space we're in. If we pop two balloons in very quick succession, the second pop will effectively mask the ringing sound caused by the first balloon, thereby making it significantly less noticeable. As we said, these are phenomena that happen every day and that we are used to, so they don't cause any discomfort. Pre-ringing, on the other hand, is a phenomenon that cannot occur in reality because it would be like hearing the reverberation before the sound that causes it. It's not possible. Moreover, unlike post-ringing, the initial pre-ringing is not masked by other sounds and is particularly noticeable. If it were possible to recreate it, the pre-ringing caused by a bursting balloon would sound like this. It would be hard not to notice it. Furthermore, one of its effects is to reduce the impact of transients, because it spreads the energy over a longer period, softening them. These reasons make pre-ringing particularly annoying and noticeable, so it's important to try to avoid it or minimize it as much as possible. A linear phase filter is necessary in all those applications where it is important not to alter the phase and the waveform of a signal, such as in an electrocardiogram or an electroencephalogram, for example. If in this type of test we filter the signal to remove background noise or external interference, it is very important that the phase relationship between the signals is maintained for an accurate reading. In actual fact, linear phase filters were originally developed for specific scientific purposes, and only later were they widely adopted for professional audio production. However, in this field, a linear phase EQ is not as indispensable a tool as it is often made out to be. This is also demonstrated by the fact that whenever it is introduced, reference is made to phase problems that a minimum phase EQ introduces, which are recognizable as gain alterations in a frequency band. In this explanation, it seems there is a contradiction. Normally, when you use an EQ, it is to correct a problem. So the assumption is that for some reason we are not satisfied with the sound we are working on. There's no reason to stubbornly preserve the phase coherence of a sound we don't like. It's like renovating an old house but being very careful to keep the cracks in the walls. In this scenario, phase distortion isn't a problem. In fact, it's the solution that allows us to achieve the sound we're satisfied with. Moreover, as we've already seen, the human ear isn't very sensitive to the absolute phase of a signal. For example, two 100 Hz waves with any phase difference sound indistinguishable when listened to on their own. However, phase differences become important when combining signals that have a phase relationship with each other, such as in parallel processing or multi-microphone recording, like with drums, for example. In these situations, it might therefore seem logical to use a linear phase EQ if you want to equalize only one of the signals. But if we use an EQ on only one of the signals and not all of them, it's because we're not satisfied with how they sound together. Even in this case, there's no reason to want to maintain the phase relationship between the signals. Furthermore, if the result of the equalization isn't pleasing, you can keep making adjustments within the context until it sounds right, compensating by ear. In this scenario, using a linear phase EQ offers no advantages. In fact, it only brings the disadvantages we've discussed. Since phase coloration isn't an issue here, a minimum phase EQ still seems like the best solution. That said, one situation where a linear phase EQ can offer some advantages is in creating a crossover. When you split a signal into different bands to process them separately, it's necessary to maintain the original phase of the signal. That way, when we put it back together, the signal doesn't suffer from phase-related distortion. Let's look at an example. This is the original signal. If we split it into three bands using a minimum phase EQ, once we recombine it, it sounds like this. You can clearly hear a difference compared to the original. Let's do the same thing, but with a linear phase EQ. The result is much closer to the original, almost identical, even though it's not exactly the same. Processors like dynamic EQs or multiband compressors should always use linear phase crossovers. Marketing often associates linear phase EQs with mastering, implicitly suggesting that they're better than other EQs. However, it's not always clear what makes an EQ suitable for mastering. If it were better, why not use it in mixing as well? The contradiction becomes even more apparent when people claim that analog mastering, which uses only minimum phase EQs, is better than digital mastering. These two statements can't both be true. Either analog mastering is inferior to digital mastering, or linear phase EQs are not the best choice for mastering. One possible explanation for why linear phase EQs are often promoted for mastering could be that, in this specific context, their inherent flaws are significantly minimized. During the mastering process, interventions are usually not too aggressive or extreme, which ultimately makes any pre-ringing effects negligible. High latency doesn't become an issue since you're working on a finished master and not on a mix that's still being created. Moreover, in mastering, usually only a few plugin instances are used, so the increased CPU load becomes negligible. These considerations strongly suggest that linear phase EQs do not offer a real advantage for mastering. On the contrary, they could actually be a significant disadvantage for mixing. If after everything we've discussed so far, you still choose to use a linear phase EQ, let's try to understand how to use it best and how to minimize its drawbacks. To do this, we need to consider the technical aspects discussed so far and find a compromise between introduced latency, CPU load, frequency resolution, and pre-ringing. As we mentioned in a previous video, subtractive equalization offers some advantages and is the most suitable approach when using a linear phase EQ. In fact, with negative gain, ringing is less than with positive gain, reducing the problem of pre-ringing. So it's better to cut than to boost. Many manufacturers of linear phase EQs recommend using their plugins mainly on the mids and highs. In fact, as we've seen, the resolution of this type of filter decreases at low frequencies. However, increasing the resolution also increases latency and pre-ringing, which becomes particularly noticeable at low frequencies. As a result, it's better to work on the mids and highs and to prefer a minimum phase filter for the lows, especially the very low frequencies. Furthermore, to further reduce pre-ringing when working on low frequencies, it's better to keep Q values low, preferably below 1. Especially near the fundamental frequencies of transients, to avoid softening them too much. Thank you. On high frequencies, on the other hand, higher Q values can be used. Additionally, it would be better to use lower-order high-pass and low-pass filters. As we've seen in audio production, linear phase EQ is therefore not better than minimum phase EQ, as is often believed. It's simply an alternative with slightly different sonic characteristics. You may or may not like it, depending on your taste. For most tasks, a minimum phase EQ does its job perfectly well. This is demonstrated by the success of thousands of great music classics produced with this type of EQ, which are still considered benchmarks for music production today. Now that you know everything about linear phase EQs, you can make more informed decisions without being influenced by marketing. Focus on what really matters. Achieve the sound you have in mind.